이우라 교수님이시고요. 이우라 교수님은 이제 학사하고 석사는 카이스트에서 하셨고요. 그다음에 박사를 이제 코넬대에서 받으셨습니다. 그래서 2012년도에 받으셨고요. 그 이후에 이제 그 경력이 이제 브로드컴에서 시니어 스태프 사이언티스트를 한 3년 정도 하시고 나서 그다음에 이제 TJ 왓슨, 그 IBM TJ 왓슨 리서치 센터에서 이제 한 5년 정도 5, 6년 정도 계시면서 다양한 활동도 하셨고요. 이제 TJ 왓슨 계시면서 이제 콜롬비아 대학의 이제 애정트 프로페서로서 이제 강의도 하시고 또 교류도 하셨던 것 같습니다. 그 다음에 이제 올해 1월에 이제 펜스테이트 유니버시티의 이제 부교수로 부임하셔서 현재 이제 연구 활동도 그 교육 활동 하고 계십니다. 오늘 강연에 잘 부탁드립니다. 감사합니다.
예, 감사합니다. 소개 감사합니다. Good morning, everyone. My name is Wooram and I'm from Penn State University, Pennsylvania, USA. It is such a great honor to be here at e-TEC talk at Seoul National University Summer 2021. And thank you again for inviting me to present my research. In this talk, I'm going to talk about overview and fundamental innovations in millimeter wave and THz circuit design and systems by utilizing wave propagation interaction. These days, you might hear some buzzwords like 5G and 6G, millimeter wave and beamforming, and these are what I'm working on. The title of my talk today is Taming Waves for Millimeter Wave THz Communications and Sensing from Phased Array to Soliton Resonance. The most project that I'm going to present here has been done at IBM and Cornell University before I joined Penn State University. Here's the outline of my talk. I'll get started with the motivation of my research and present fundamental challenges in silicon-based high-frequency RFICs, and then I'll talk about how to engineer wave propagation and interaction in linear and nonlinear medium to overcome challenges, which will lead to innovations in IC and system level. First part of my talk will cover the IC innovations. Using this concept, I'll discuss wideband tunable delay line and parametric oscillator, which is the first time passive frequency division in CMOS and Soliton resonance for very sharp pulse generation in CMOS process. The second part of my talk will talk about the millimeter wave phase array system for the application of 3D real-time imaging radar. After that, I'll briefly touch on my future direction, then conclude my talk. Waves are everywhere in our daily life. Traffic wave formed by density of cars on highway, sea wave generated by wind and gravity, and sound wave is created by instrument. Very often, we try to tame waves for our purpose. The violin is elegantly engineered to generate sounds at frequencies which is most sensitive to our ears. There are waves which do more useful things for us. Electromagnetic wave delivers video streaming data to our cell phones. It delivers sensing information such as gesture recognition, and it also transfers power to charge many IoT devices. In this system, we rely on wave propagation interaction. And next important question would be, how do you make waves do better job for higher data rate and higher radar resolution and more focused energy? One obvious direction is using higher frequency or shorter wavelengths. This is why we are so much interested in millimeter wave and THz frequencies. Millimeter wave and THz frequency has the wavelengths less than 10 millimeter, which corresponds to higher than 30 hertz of frequencies. Millimeter wave and THz frequencies provide wide fractional bandwidth, which will provide larger channel capacity. It also provides higher radar resolution thanks to smaller wavelengths and wider bandwidth. And it also provide narrow beamwidth for given antenna aperture to have a better focused beam. With these advantages, I strongly believe that mmWave and THz technology will be a key enabler in the 5G and beyond the 5G era. Figure at the bottom shows that wireless technology evolution starting from 1G in 1980. We are at the beginning of 5G. Verizon Wireless already deployed many base stations using mmWave phase array developed by IBM and Ericsson in several cities in the US. After 5G, 6G is coming to accommodate ever-increasing wire data capacity and enabling many exciting applications such as VR and AR and etc. And in the 6G era, everything and everyone will be connected using ultra-wideband network enabled by mmWave THz technology. And this will fundamentally change how the human beings lives and plays and learns. And the next important question is, how do you make this mmWave and THz technology less expensive and smaller device size to be more accessible to everyone and every device? The answer is silicon integration. As we all know, rapid development of computing and communication system was possible thanks to advance in silicon technology. Like other domains, THz and mmWave technology can take advantage of silicon integration to enable miniaturization and mass adoption. As you can see at the top figures, these two figures compare 60 GHz radio system implemented in 3.5 lumped element and silicon integration. While they do the exactly same functionality, cost and size with the silicon integration are significantly reduced by more than a factor of 100. However, silicon transistor has a limited saturation output power and limited maximum operation frequency than counterpart in 3.5 technologies. This figure shows the saturation output power as a function of frequency for different processes. As you can see, the saturation output power drops as frequency increases, and CMOS has only 30 dB lower power than 3.5s. This is because of limited breakdown voltage and lower cutoff frequency, and this clearly shows that power generation in silicon is challenging. In addition to limited power generation, a silicon transistor has limited maximum operation frequency and noise performance. As shown in the figure on the left, the maximum operation frequency as a function of channel length and emitter width for different processes. Thanks to Moore's law, so as the channel length shrinks down, we can get higher Fmax. However, still transistor in silicon has a lower Fmax. If you look at the maximum available gain for given Fmax, it is inversely proportional to F squared. For instance, if the silicon technology has the Fmax of 200 GHz, the maximum achievable gain at 100 GHz is limited to 6 dB. Figure on the right shows a noise figure as a function of frequency for different processes. Noise figure is getting worse as frequency increases due to smaller transistor gain and increase the loss of passive components such as transmission line and inductors and capacitors. This means that the sensitivity of silicon-based receiver is getting worse as the frequency goes higher. Another challenge in high-frequency IC design. As the frequency goes higher, the wavelengths getting smaller, and at some point, the physical size of the circuit component becomes comparable to wavelengths. That means we cannot use basic circuit theory based on KCL, KVL to analyze circuit behavior. And now we need to look at the circuit from the wavepoint perspective, based on these wave equations. This wave equation is very similar to mmWave propagation equation derived by Maxwell's equation. As an example of this wave property on the circuit component, we can briefly look at this CMOS transmission line with a length of 0.35 millimeter. And one end of this transmission line is shorted. When you observe the input impedance of this short transmission line, at lower frequency, it presented very low impedance. But as the frequency goes higher at some point, it presents very high impedance like open. This clearly shows the wave nature of the circuit at high frequency, which makes the circuit design more challenging. To overcome these high frequency challenges in silicon, we can place many identical components and let them work together and together so that they can be powerful together. As an example, we place the n-element transmitter and n-element receiver. For transmitter, when you have n element, the radiation power is increased by factor of n squared by factor of n from the linear combination of output power and another factor of n from the more focused beam. So at receiver, signal to noise ratio is also improved by factor of n because the signal is combined coherently while noise are averaged. From this link budget, we can know that link budget is significantly improved by factor of the n to the 3. I just want to bring this very interesting analogy between this army of ants and single Steger beetle. So army of ants can be stronger than the single Steger beetle when they work together. Using this concept, here are the project that I completed at IBM. I worked on 94 GHz phase array with the 64 elements for 3D real-time imaging radar, which I'll dive into in the next few slides. And then I also worked on the 24 to 30 GHz phase array for the application of 5G mobile communication. To overcome high-frequency challenges in silicon, we can also look at fundamental change of IC design utilizing wave propagation. Many of my research topics are inspired by interesting phenomena in physics and nonlinear optics. Some of the examples are broadband delay control by utilizing distributed Miller effect and parametric oscillation, which is the first time passive frequency divider in CMOS, and Soliton resonance to generate record-breaking pulse width in CMOS. By utilizing wave propagation and interaction in linear and nonlinear medium, we can achieve new functionality and lower noise and high frequency beyond the conventional ICs. Next, I'm going to talk about a new way of controlling wave propagation to implement wideband tunable delay line for the application of phase array. Tunable delay element is critical for phase array for accurate beam steering. This tunable, the narrow band phase shifter can do the exactly same functionality for very narrow fractional bandwidth. However, to support wide bandwidth, we need a true time delay, which provides the phase shift linearly changed across the frequencies. These two tunable delay elements are desired to have the following characteristics: high time resolution for accurate beam control, wide signal bandwidth, and constant insertion loss during delay control to make the calibration much easier. Wideband delay can be generated using transmission line. Wave propagation in transmission line can be defined using two parameters, propagation delay and characteristic impedance. And both parameters are defined using inductance per unit length and capacitance per unit length. And propagation delay is a function of the length of transmission line and L and C. That means when you have longer transmission line length and larger inductance, larger capacitance, we have longer propagation delay. The next question is, how do you make the delay line tunable while we can keep the insertion loss and characteristic impedance constant? One easy way would be to make the inductance and capacitance switchable. One implementation example is shown on the right. So as you can see, the ground plane is switchable to control inductance and capacitance. By changing capacitance and inductance in the same direction, we can maintain characteristic impedance to be constant while we achieve the larger delay tuning range. However, because of this discrete property of switching, it has this limited delay resolution and limited bandwidth. To achieve better resolution, we need a continuous tuning of capacitance and inductance. For continuous capacitance tuning, you might come up with most vectors. However, most vectors present a very large loss variation during capacitance control. Instead, I propose to use Miller effect to tune capacitance continuously. As you might remember from analog circuit design class, so when we have inverting amplifier and we have coupling capacitor between input and output, the input capacitance contribution from this DC is boosted by gain of this amplifier. That means by changing the gain of amplifier, we can tune the input capacitance. The next question is, how do you tune the inductance continuously to achieve larger tuning range while we keep the characteristic impedance constant? I found the answer from beautiful duality between inductance and capacitance and current and voltage. In the Miller effect, we found that coupling capacitor can be boosted by voltage gain. Likewise, we can predict the existence of Miller inductance from the mutual inductance can be boosted by current amplification. In other words, input inductance contributed by mutual inductance can be changed continuously by tuning current gain. Now we have continuous tunable capacitor inductance, and the next question is, how can we combine these two into a single architecture? To do that, I propose a coupled transmission line with a variable gain amplifier. This variable amplifier, gain amplifier, provides variable voltage and current gain. For capacitor tuning, utilizing this coupling capacitor and voltage gain, capacitance can be tunable. For the inductance tuning, we utilize the current gain and these coupled inductors to get continuous inductance. By utilizing this architecture, we can achieve wide and continuously tunable delay with a constant characteristic impedance. The prototype of this distributed Miller effect tunable delay line is fabricated in 45 RF-SOI CMOS processes. To achieve 180-degree phase tuning range at 30 Hz, we cascaded 4 stages of this Miller effect tunable delay lines. Since the variable gain amplifier is controlled with this differential pair, the delay can be modulated with a very high frequency, more than 1 GHz, while keeping insertion loss while keeping the insertion loss and characteristic impedance constant. This is a measurement result. Figure on the left shows the measured phase shift across the frequency for different control voltages. As you can see, the proposed delay line presents the linear phase shift across the frequency, and we could achieve more than 180-degree phase tuning range at 30 Hz. Figure on the right shows the phase as a function of control voltage at different frequencies. As you can see, the proposed delay line provides linear and continuous phase tuning as a function of control voltages. We also measure the insertion loss across the frequency for different control voltages. This insertion loss is very consistent over phase tuning, and the variation is very minor, the plus minus 0.3 dB at 20 GHz and plus minus 0.5 dB at 30 Hz. Input insertion loss is also very consistent across the different control voltages, and this is thanks to constant characteristic impedance from the simultaneous change in inductance and capacitance. Next, I'm going to make your life even harder by introducing nonlinear wave propagation. However, at the end, I hope that you can find this nonlinear phenomenon have much richer property than the linear cases, and which will lead to many intriguing IC innovations. To have nonlinear wave propagation, we need a nonlinear medium. Nonlinear medium can be formed using voltage-dependent capacitor along with the inductors, and it can be formed in one-dimensional or two-dimensional spaces, and its shape can be rectangle, hexagonal, or triangular, but basic principles are the same. When the inductance and capacitance does not change abruptly, we can easily define propagation constant and characteristic impedance at any point of this lattice. That means we can engineer this medium to get desired response. It is noted that the cutoff frequency of this lattice can be very high beyond the cutoff frequency of the transistor. When the voltage-dependent capacitor has a capacitance proportional to voltage, the medium will present second-order nonlinearity, which will initiate many interesting nonlinear phenomena. Among many nonlinear phenomena, I'm interested in Soliton generation and parametric amplification. Nonlinear wave equation can be reduced to KdV equation, which explains Soliton generation. When you apply broad pulse into nonlinear medium, under certain condition, particle-like waveform is generated over propagation from the balance between the dispersion and nonlinearity. Parametric amplification is also a result of this second-order nonlinearity. When you apply signal and pump at different frequencies, energy at higher frequency is transferred to the lower frequency for amplification. This amplification process is fundamentally different from transistor-based amplification, since it is not limited by maximum operation frequency of transistors. To get better understanding of this parametric amplification, we can look at swing in the playground. There are two ways of increase the swing. The one way is you can have someone to push your back, or you can rely on yourself. Like you can move your body at twice the frequency of swing. The governing equation of the swing can be written as this. And we are electrical engineers, and we can find out exactly same system as these swings. Right? So without solving a nonlinear equation, we can understand that by changing capacitance, we can increase the voltage as we move our body to increase the swing. To understand better on this LC resonator-based parametric application, let's look at this slide. In this LC resonator, let's assume that we have initial sinusoidal wave. When this wave is maximum, we increase the distance between these two plates, and it will lower the capacitance. According to charge conservation theorem, the decrease in capacitance will increase the voltage. When the voltage crosses the zero, we return this plate to the original state, but in this case, since the voltage is zero, it doesn't need any work to do. By repeating this process, we can have continuous amplitude increase amplification over time. And this is called parametric amplification. We can extend this parametric amplification in an LC resonator to transmission line, which is which consists of series of many LC resonator. If you look at Gorboni equation of this LC resonator and transmission line, they are exactly dual by switching the time with the space. From this duality, we can predict that there will be parametric amplification over wave propagation, like we see parametric amplification in a LC resonator over time. By utilizing distributed parametric amplification over transmission line, I propose a distributed parametric oscillator for passive frequency division. This parametric oscillator consists of 4 LC sections, and both ends are connected to make a reflection. When you apply pump signal from the left end, the ambient noise at half of this pump frequency will be amplified through the parametric amplification and traveling back and forth between these two reflected ends. In the end, it will generate a stable oscillating signal at half of pump frequency. This process is very similar to how the laser works. Since the input signal is common mode for these two lines, while the output signal is differential, the way these two signals look at the ends are different. Utilizing this different standing wave formation, we can suppress the input frequency at the output port, even for the single-ended output. This system is exactly the same as what we observe in swing. Basically, by injecting pump frequency, we can generate the half of frequency without any amplifier in the system. We designed the parametric oscillator as a prototype in 0.13 microsiemens process to operate at input frequency of 20 GHz. Figure on the right shows the measurement result. When the input amplitude is beyond 400 millivolt, the output amplitude comes out at half of frequencies. As you increase the pump amplitude, we see the higher output amplitude because we are getting the more energy from the input. And figure on the right shows the output waveform in time domain. And this gray line is input signal. And this red line is differential output. And this the black line is single-ended output. This work demonstrated the first time passive frequency divider in CMOS without any transistors, and which means it does not consume no static power and superior noise performance. So far, we looked at the case that energy at higher frequency can be transferred to the lower frequency. Now, let's look at the other case that energy at lower frequency is transferred to higher frequency. And one of the popular examples is pulse generation. So when we inject a sinusoidal signal at omega 0, into a nonlinear medium, it will generate multiple different harmonics, and in time domain, it will generate pulse. Since this process is not limited by transistor cutoff frequency, it can generate very wide bandwidth pulse signal. This wideband pulse signal is useful in many real-world applications, such as wideband pulse radar and high-speed sampling and spectroscopy. For this purpose, I propose a two-dimensional nonlinear lattice. We discovered that under certain conditions, two incoming waves can be combined in a way that outgoing wave has much higher amplitude and much higher frequency than superposition of the two incoming waves. This is particularly interesting since the passive medium cannot boost energy. But this was possible because energy was localized in time and space. And this is called Soliton resonance. We can find a similar phenomenon in nature too. So you can see that when the two waves meet together in the diagonal direction, we have sharp wave. To prove this energy localization based on the energy conservation approach, we did some theoretical work. And I'm not going through the details of the theory, but we could find that the output amplitude is output amplitude increased with the input amplitude in a superlinear fashion because of this energy localization thanks to nonlinearity. We also did some numerical analysis based on the wave equation, discrete wave equation, and n by n nonlinear LC lattice. And figure on the right shows the simulation result. You can see that two waves are generated from the left and the bottom. And when they meet together in the diagonal direction, it generates very sharp wave in diagonal direction. I fabricated this nonlinear lattice in 0.13 microsiemens process. And the input signal is applied from the left bottom, and it will generate the wave from the left end and from the bottom throughout this distribution network. And when these two waves are meet in the diagonal direction, it generates very sharp waves. Figure on the right shows the generated waveform and without the embedding any losses in the measurement setup. As you can see, it generates the full wave, the pulse width less than 10 picosecond when we inject a 20 GHz sinusoidal input. Here's the measured performance in pulse width and the boosting ratio. As we increase the input amplitude, because of energy localization in time, the pulse width shrinks down. And finally, in the end, it approaches the measurement limit, which is 7.2 picosecond. Figure on the right shows the boosting ratio. Boosting ratio is defined by output pulse width amplitude over input sinusoidal amplitude. So ideally, in linear lattice, we should see 2 as a boosting ratio, but because of the loss, so we only see 1.4. But in the nonlinear wave, nonlinear lattice, as we increase the input amplitude, because of energy localization, the boosting ratio can go beyond this amplitude, achieving up to 2.4. When this work was published, this work demonstrated the narrowest pulse width achieved in any CMOS processes with a high pulse amplitude. Next, let's switch our gear to discuss a millimeter wave phase array for the application of 3D real-time imaging radar. As we briefly discussed in the beginning, phase array can significantly improve link budget. When you have an element phase array transmitter and receiver, transmitter radiation power grows by n to the 2, and RX SNL is also improved by a factor of n. So overall link budget is dramatically improved by n to the 3. And this is why phase array is so important at millimeter wave and terahertz frequencies, where the transistor gain and power and noise is getting worse. Figure on the right compares the 16 element and 1024 element beam pattern. As you can see, the radiation power is improved by 36 dB. In addition, we have more focused beam, which is good for directional communication or higher angular resolution in radar applications. In addition to this significant link budget improvement, another important property of this phase array is beam steering. And this beam steering can be implemented by adding tunable phase shifters at each front end. And the next slide will show you the fundamental principle of this beam steering. So let's say we have these 4 elements, and each element has the same delay. Then when the radiation from each element is combined in the direction, also going to this array. When we change the time delay progressively, then this beam can be steered in different direction to form a different link. To reduce the side lobe, which is the undesired energy radiation, we can taper the amplitude of each element, and this is called amplitude array tapering. By utilizing this beam steering characteristic and narrow beam width, we propose a 3D imaging radar at 94 GHz frequencies. This imaging radar consists of 94 GHz TX and RX phase array modules and radar signal generation, acquisition, and processing blocks. This phase array scans a very sharp beam in 2-dimensional space, and each beam is modulated with the radar signal such as FMCW. By combining this information, we can construct 3D imaging. This 3D imaging radar has many exciting applications, such as automotive radar and gesture recognition and industrial radar and security and many others. When this imaging radar is combined with AI, it can be more even powerful. 94 GHz phase array has several advantages over phase array at lower frequencies. This figure shows phase array at 28 GHz and 60 GHz and 94 GHz. As you can see, the size shrinks down proportional to lambda square, which means we can accommodate more elements for given package or antenna size. And 94 GHz frequency provides much wider fractional bandwidth and smaller wavelengths to have higher radar resolution. However, there are several challenges to implement 94 GHz phase array ICs. We need a high resolution phase shifter for achieving fine beam steering control. Gain and phase need to be controlled orthogonally to make calibration easier. To avoid any polarization misalignment loss, this phase array needs to support dual polarizations. To accommodate a large number of elements, the structure needs to be scalable. All this functionality needs to be squeezed into very small module, which will increase the heat density dramatically. That means IC needs to operate robustly up to very high temperature. To meet all this, the requirement, the IBM and Aselsan in Turkey, in collaboration, developed this 94 GHz phase array TX and RX ICs. TX phase array IC consists of 16 phase shifting transmitting front end and 1-to-16 splitter and a converter and IF baseband. And to generate LO signal, it also has PLL. RX phase array has the 32 phase shifting RX front end and down converter, and PLL, and IF baseband. And these two chips have the very complicated digital circuitry to enable complex digital calibration and the fast and regular beam steering mode operations. Here is a summary of measured IC performance in TX and RX. Transmitter present saturation output power of around 8 dBm, and RX present noise figure less than 7 dB at room temperature, which is comparable to state of art in other W-band phase array. And it also operates very reliably up to 105 degrees, both for TX and RX, which is the first demonstration of this high temperature operation. And both TX and RX provides 1.6 degree phase resolution, which is almost one order better than other W-band phase array. And it also provides phase invariant gain control, which is around plus minus 0.5 dB. And both ICs have very high level of IC integration. The next question is, how do you make this phase array more scalable to accommodate more elements? Here is our proposal. We start with the transceiver IC with the 16 transceivers. And we place these 4 of these ICs on the antenna in packaging using flip chip bonding. You can see that backside of this packaging, we assemble RFIC, and the other side we have antennas. And by placing this package on the PCB, we can further extend number of elements it can support. However, there are challenges. Chip area needs to be smaller than, chip area per element needs to be smaller than lambda over 2 square, which is the antenna spacing, to meet 100% antenna field. And this condition can be more challenging as the frequency goes higher, since the wavelength shrinks down while the size of IC is almost constant. Another challenge is signal combining and splitting and the network design and clock synchronization among the different ICs and packages. Here's the measured beam steering result using this 64 elements of TX and RX module. Figure in the middle shows the beam pattern for different setting of phase shifter to implement 5-degree step beam steering. We found that this measured beam pattern is very close to what you can expect from the theory. And figure on the right shows the very fine beam steering capability. The resolution is almost 1 degree, and this was possible due to the very fine tuning capability of each phase shifter. The measured 64 element EIRP is around 39 dBm. Here's the implemented 3D imaging radar utilizing phase array module. High-speed FPGA and DAC generating 1 GHz of radar signal, FMCW, and this signal is converted into IF frequency, which is 10 GHz, and that goes into TX. And TX scans a beam in 2-dimensional space. And reflective wave is collected from the receiver. And by doing the bidding operation, and we can generate the IF signal, and that goes into ADC. And for radar processing, it goes into the PC in the end. This FPGA controls the beam scanning of this phase array and also radar signal generation, acquisition, and processing in synchronization. The total time per one direction scan, which includes 64 element beam steering and radar signal generation, acquisition, processing, is less than 100 microseconds. We demonstrate the function of this 3D imaging radar by using these 2 target corner reflectors, left top and right bottom. And figure on the right shows the 3D imaging result by using our imaging radar. And we also have done real-time real-time imaging the experiment to track the fastly moving drones in antenna chamber. But at this moment, the video is not available, so that I cannot present it in this talk. Next, I'll briefly touch on future direction of my research. To realize the fully connected world in the 6G era, my key research directions are the larger channel capacity and higher energy efficiency and AI convergence. In line with this, my research group will work on fundamental innovation in mmWave and THz IC packaging system. As a one direction, future direction, to pursue larger channel capacity, my research group is working on mmWave THz scalable phase array toward the 1 terabit per second transmission over 100 meters. This requires fundamental innovations across the different hierarchy of system, IC, antennas and packaging, and system and test bed. In the end, we like to complete the module with the software interface so that we can build the 6G test bed in collaboration with other groups. We can also, we are also interested in looking at new IC design methodology inspired by other fields such as optics and physics and nonlinear optics to achieve performance beyond transistor limit. For instance, we can achieve amplification beyond the transistor cutoff frequency by getting energy from light. And you can see that there is a nonlinear coupling between the electrical signal and optical signals throughout this Schottky diode. And the other example is there's an interesting idea of time stretching ADC in optics. So to achieve the fast speed analog to digital conversion, we can borrow that idea to implement it in electrical domain. I'll conclude my talk. In conclusion, mmWave and THz technology is profoundly important to realize the next generation communication sensing in the era of the 6G. And I proposed a new IC and system designs inspired by wave propagation interaction in linear and nonlinear medium at mmWave THz frequencies. And my research group will work on fundamental research to achieve 1 terabit per second channel capacity and high energy efficiency and AI THz convergence to realize 6G era. Okay, this is the end of my talk.
네, 감사합니다. Thank you very much. 저기 질의응답은 뭐 간단하게 한국말로 하도록 하겠습니다. 혹시 질문 있으신 분들이 있으시면 질문 부탁드립니다.
네, 우리 이 교수님 고생 많이 하셨습니다. 예전에 발표한 데에 비해서 그 앞부분이 약간 바뀌었다는 느낌도 좀 있는데 옛날에 솔리톤 했었나요?
예, 예전에 서울대 세미나 할 때는 좀 더 IBM에서 했던 일을 포커스를 했는데요. 이게 mmWave phase array IC랑 시스템에 대해서 포커스를 했는데 이번에는 좀 더 이렇게 제가 PhD 때 했던 일이 이제 예를 들어서 많은 그 아이디어들이 있는데 nonlinear optics나 피직스에 그런 많은 아이디어가 있는데 그런 아이디어를 우리가 서킷 디자인에 가져올 수는 없을까? 그렇다면 우리가 컨벤셔널한 트랜지스터 베이스 기반의 회로의 그런 퍼포먼스를 뛰어넘을 수 있지 않을까 하는 그런 연구를 했었거든요. 그래서 그쪽도 좀 집어넣었습니다.
네, 잘 알겠습니다. 거기 그 밀리메타파 뭐 IC가 실리콘으로 밀리메타파 어떻게 보면 트랜시버 리시버 트랜시버를 만들어서 실험도 하고 막 그러는데 전체 만들었던 시스템에 뭐 이피션시 이슈나 열 문제는 없어요. 어떻게 해결하나요?
네, 되게 좋은 질문이신데요. 아까 말씀드렸던 것처럼 제가 지금 슬라이드를 넘기겠습니다. 좀 딜레이가 있어서 잠시만요. 예. 여기서 보시다시피 지금 그 IC 디자인 그 프리퀀시가 점점 높아지면은 그 웨이브랭스가 점점 작아지기 때문에 근데 보통 보면은 페이즈 어레이에서 안테나 스페이싱은 람다 오버 2로 디파인되지 않습니까? 그러니까 프리퀀시가 증가하고 웨이브랭스가 감소를 하면 이 패키징 사이즈는 점점 이렇게 줄어들거든요. 근데 그 저희가 IC 사이즈를 본다면 그렇게 IC 사이즈는 이 그 웨이브랭스에 따라서 이렇게 줄어들지가 않습니다. 그래서 결국은 우리가 줄어든 패키징에 IC를 어떻게 인테그레이션 할지 그리고 점점 패키징 사이즈가 줄어들기 때문에 아까 말씀하신 대로 힛 덴서티 문제가 되게 중요한 문제가 될 수 있는데요. 그래서 저희가 이 시스템을 데몬스트레이션 할 때는 저희가 팬을 달았거든요. 그 IC 뒷면에 이렇게 패키징을 보시면 아마 이쪽에 보였던 것 같은데 여기 있어요. 저희 히싱크도 여기 이렇게 달고요. 지금 보시면은 이게 안테나의 패키지가 이렇게 온탑에 있고 그다음에 중간에 RFIC가 있고 그다음에 RFIC 뒷면으로 히싱크가 있고요. 여기에다가 팬도 답니다. 그래서 우리가 쿨링을 해줄 수 있도록. 그래서 이제 그 하이 프리퀀시 갈수록 칩 사이즈는 그대로 되고 패키징은 줄어들고 그렇지만은 그 IC의 파워 에피션시는 점점 나빠지지 않습니까? 그래서 예를 들어서 똑같은 아웃풋 파워를 제너레이션 하더라도 우리가 DC 파워 컨섬프션은 점점 증가를 하는데요. 그래서 아까 말씀하셨던 힛을 어떻게 우리가 디스페이트 할지는 정말 그것도 중요한 그런 토픽인 것 같습니다.
예, 잘 알겠습니다. 우리 우정석 교수님 혹시 질문 없으세요?
네. 유랑 교수님 좋은 발표 잘 들었습니다. 예. 저도 질문을 뭐 간단하게 드리면 그 뒤에 그 원테라 BPS 식세지도 말씀을 하셨고 이런 부분에서 보면 많은 엔지니어들이 여러 가지 고민들을 하고 있는데요. 그 서두에 그 실리콘을 100GHz에서 6dB 정도 파워가 제한일 거다 이런 언급을 하셨던 것 같긴 한데 그래서 그 뭐 시머스와 화합물 이런 관점에서 그 시머스로 할 수 있는 주파수 바운더리를 그 최근에는 어느 정도로 보고 있고 뭐 이런 부분에 대해서 좀 의견을 주실 수 있을까요? 예.
그 우리가 시스템을 구성할 때 가장 펀더멘탈한 블락이 그 앰플리파이어라고 볼 수 있는데요. 이제 제가 그 실리콘 시모스 기반의 앰플리파이어를 최근에 앰플리파이어를 본다면 아직까지는 한 200 초반까지는 200 GHz 초반까지는 시모스 앰플리파이어가 가능한 것 같습니다. 그래서 예를 들어서 그 아까 지적하셨던 것처럼 그 싱글 스테이지가 그 제너레이트 할 수 있는 게인은 제한되어 있기 때문에 그 많은 스테이지를 써가지고 그 대신 파워 에피션시는 떨어지지만 게인은 어느 정도 만들 수 있는 그래서 200 초반까지는 제가 보기에는 시모스로 가능한 것 같고요. 앰플리파이어로. 그런데 만약에 우리가 높은 파워를 RF 파워를 제너레이션 해야 된다면 그 TX를 위해서 그런다면은 제가 요즘에 보는 좀 인터레스팅한 했던 어프로치가 그 UC 산타바바라의 그 로드웰 그룹에서 했던 건데요. 이건 컨버터까지는 CMOS로 하고 그 다음부터는 3.5 파워 앰플리파이어를 쓰더라고요. 그러니까 그렇게 한다면 140GHz에서도 한 16dBm 그 정도까지는 세션 파워를 얻을 수 있었던 걸 봤습니다. 그래서 이게 제가 보기엔 앰플리피케이션까지는 괜찮은데 이피션트한 파워 제너레이션까지는 시모스한테는 그 100GHz가 넘어가면 좀 무리인 것 같습니다.
네, 감사합니다, 교수님.
네.
제가 질문을 좀 해도 될까요? 예. So, 두 가지 좀 이거는 시스템 관련한 좀 프랙티컬한 질문인데요. 지금 보면 그 중간에 그 페이즈 쉬프트 레이트를 1GHz 이상으로 하는 걸 가능하다는 걸 얘기를 하셨는데 그게 시스템상에서 그 정도 사양을 요구를 하는 게 지금 있나요? 아니면은 그냥 퓨처 프루프한 관점에서 거기까지 설계를 하시는 건가요?
그건 되게 좋은 질문이신데요. 되게 인터레스팅한 어플리케이션 중에 하나가 그러니까 페이즈 어레이의 인터레스팅한 어플리케이션 중에 하나가 그러니까 피지컬 시큐리티를 임프루브하는 것도 있거든요. 그러니까 데이터를 RF 인풋으로 하는 것이 아니라 그 페이스 시프터를 빠른 속도로 모듈레이트해서 그러니까
예.
동시에 이제 동시에 컨트롤하는 거죠. 빔 스트링 디렉션과 그다음에 데이터를 이제 그럴 때 좀 쓸 수 있을 것 같은데 교수님 말씀하신 대로 좀 더 디테일한 시스템 임플리멘테이션은 좀 더 많은 연구가 필요한 것 같습니다.
그 비슷한 질문인데요. 그리고 아까 그 스티어링 앵글 레졸루션도 보면은 뭐 1디그리 뭐 이런 거를 데모를 하셨는데 지금 비미스가 15디그리인데 그걸 1디그리로 스티어링을 하는 게 그러니까 뭐 캘리브레이션용으로는 제가 볼 때는 그게 꼭 필요한 거긴 한데 그러니까 실제 시스템 상에서 그런 레졸루션을 필요로 하는 애플리케이션이 있을까요? 뭐 아까 말씀드린 것처럼 아마 시큐리티 쪽으로 있을 수 있을 것 같긴 한데
그거 되게 좋은 질문이신데요. 말씀하신 대로, 그러니까 엘리멘트 수가 많지 않아서 빔 위드가 클 때는 제가 보기에도 이렇게 빔 스티어링 레졸루션이 그렇게 작을 필요가 없는데요. 예를 들어서 우리가 6G 페이저 어레이를 사용을 해본다면 이제 우리가 더 많은 숫자의 그런 엘리먼트가 필요하지 않습니까? 그리고 예를 들어 6G에서는 그 실리콘에서 제너레이트 할 수 있는 파워가 제한되어 있고 노이즈 퍼포먼스도 제한되어 있으니까 저희가 더 많은 엘리먼트가 필요하거든요. 근데 더 많은 엘리먼트를 쓰다 보면은 그 빔 위드가 그 넘버 오브 엘리먼트 인버스리 프로포셔널 하잖아요. 그러니까 6G 페이즈 어레이를 그 좀 예상되는 논문들을 본다면 대부분 보실 수 있는 게 빔 위드가 아마 0.5 디그리, less than 1 디그리 된다고.
그렇죠.
그럴 때는 아마 이렇게 되게
그러니까
액큐리트한 빔 컨트롤이 필요할 것 같습니다.
엘리먼트 넘버랑 그러니까 빔 스티어링 레졸루션하고 코릴레이션이 없으니까 그냥 스케일이 안 되니까 그게 그게 필요할 수도 있겠네요. 죄송합니다. 딱 하나만 더 질문을.
괜찮습니다.
죄송합니다. 시간이 다 됐는데 그 하나는 이제 그 디바이더 그 non-linear 그 트랜스미션 라인 가지고 디바이더 구현하신 거에 보면 이제 궁극적으로는 그 non-linear capacitance 가지고 그러니까 프리퀀시 컨버전 디바이스를 만드신 거잖아요. 그러면은 그게 파워 게인이 어떻게 됐나요? 이게 궁극적으로는 아마 맨리로 바운드리 때문에 파워 자체는 증폭은 안 될 것 같은데 프리퀀시가 낮아지면 그 혹시 파워 관점에서 인풋 아웃 파워 컨버전 게인 같은 데이터가 있나요? 제가 못 본 것 같았어요 프레젠테이션을.
일단 게인은 있고요. 그러니까 게인이 있으니까 우리가 어실레이션을 이제 잘 생각을 해보시면 이제 저희가 레조네이터를 빌드했잖아요. 근데 만약에 게인이 1보다 작다면 이 레조네이터가 어실레이터 될 수는 없잖아요. 왜냐하면은 그 게인이 이런 레조네이터 러스를 컴펜세이트 할 수 있을 때 어실레이션이 발생하지 않습니까?
근데 기본적으로 지금 그 시스템 안에 들어가는 파워가 인풋 파워, 그러니까 인풋 파워가 그 RF 시그널에서밖에 없는 거잖아요. 그러면 아웃풋, 그러니까 그다음에 에너지 컨저베이션 때문에 아웃풋 파워가 그러니까 결국 포톤이 한 프리퀀시에 들어가서 낮은 프리퀀시에서 나오는 거니까 에너지는 기본적으로 그러니까 맥시멈 절반이 돼야 될 것 같거든요.
제가 이제 질문 포인트를 알았네요. 그러니까 제가 설명했던 그 질문은 그러니까 시그널 퍼스펙티브에서 봤을 때 게인을 그냥 시그널이 얼마나 그 증폭이 됐는지를 봤을 때 이제 증폭이 되는 건 맞고요. 패러메트릭 애플리케이션에 의해서. 그렇지만 말씀하신 포인트는 전체 에너지를 놓고 봤을 때 이피션시 건지를 물어보시는 거죠. 예를 들어서 전체 에너지 컨섬프션은 이제 펌프 에너지 더하기 뭐 시그널 에너지 더하기로 본다면 그러면 어떻게 에너지 이피션시가 그렇게 정의를 하시는 건가요? 아니면 어떻게?
근데 그 디바이더에서는 그 펌프가 따로 없었지 않나요? 디바이더 펌프가?
이제 제가 포인트를 알겠네요. 그러니까 예를 들어서 이 파라메트릭 어실레이터를 사용한 프리퀀시 디바이더를 일반적인 트랜지스터 베이스드 된 프리퀀시 디바이더 비교를 할 때 그럼 우리가 에너지 이피션시를 output power over the entire power dissipation으로 정의를 할 수 있고 이제 예를 들어 트랜지스터 베이스드 디바이더는 DC 파워 컨섬션 있잖아요. 트랜지스터에. 근데 그런 걸 생각을 고려를 했을 때 이 디바이더가 트랜지스터 베이스드 디바이더 더 이피션시한지를 여쭤보신 거죠?
그 펀더멘탈 리밋이 있잖아요. 그 맨리로 릴레이션십 때문에 결과적으로는 파워 입장에서는 해프가 될 수밖에 없는데, 그러니까 그게 그게 그 측정하신 부분이랑 또 매치가 되는지 뭐
예.
그런 게 좀 궁금해요. 아니,
아, 예.
나중에 제가 한번 이메일을
예,
드리고
근데 되게
뭐,
좋은 질문이신데 제가 그 데이터는 없습니다. 얼마나 이게
예.
프로세스인지. 근데 되게
오래전에 하신 일이라서.
질문이십니다. 예, 되게 좋은 질문이십니다. 근데 예.
예, 감사합니다.
네, 이제 저희가 딱 정확하게 1시간이 돼서 네, 이제 마무리를 하고 네, 다음으로 넘어가도록 하겠습니다. 예, 이유랑 교수님 감사합니다.
예, 감사합니다.
네, 다음 강연은 이제 최우열 교수님께서 이제 해주신